Okay, so now that you're getting pretty decent at lenses, it's time to talk about pieces of equipment that have more than one lens, like microscopes or telescopes or binoculars. Okay, so a microscope has two lenses. It has one up here by where your eye is, so this is your eye looking down in the microscope. And then there's like this long shaft, and then you have, usually the piece where you turn it around and pick like which lens you want, at the bottom. I haven't seen the ones in Miss Holyoke Walsh's lab lately, but usually there's like three, and you can change it depending on what magnification you want. I'm just looking to see objective lens and eyepiece. So this one is the eyepiece. And the one down here is called the objective lens. Eyepiece lens, objective lens, right? And so the cool thing that happens is, so this lens down here is the first one that the light from the slide passes through, right? So you have a slide here with some kind of a specimen on it. And so then this lens will form an image, and that image will form like somewhere in here. And I'm assuming it's real, so I did it upside down. So this image, which is image number 1, then will become the object of lens 2. Okay, so the objective lens is the first lens, the eyepiece is the second lens. So this is object 1, the slide. Okay, and so this becomes image, then you get your image 1, but image 1 then becomes object 2. So the image of the first lens becomes the object of the second. And so now the second lens is going to focus it and create an image, and that image might be like up here somewhere. And because it's virtual, this one is, how do I know? Because it's right side up compared to its object. Oops, this is not object 2, this is image 2. It's because I was saying the word object. Image 2, okay? So the trick here is that the image of one becomes the object of the other. So this would be like a microscope, same idea in a telescope. Binoculars are really just two telescopes. Okay, you could have a combination of both convex lenses. You could have a convex and a concave. I don't know that you would have two concaves. And remember, so they might get flipped, they might not get flipped, depending on if it's real or virtual. Maybe the easiest way for you to see how this would work is for us to do an example. So example 1. So it's going to be, let's say, a microscope, and I'm going to draw it. Well, I guess I could draw it this way. I was going to draw it the other way. So here's one lens, and they're both convex lenses. Here's the other lens. Here's my object. Okay, so in the question, it would probably tell you the distance between the lenses is 40 centimeters. Okay, and it'll tell you that the focal length of the first lens is 6 centimeters. And that the object, DO, for the first lens is 8 centimeters from the lens. Okay? And then it would have to tell you the focal length of the second lens, and the focal length of the second lens is 12 centimeters. Okay? And so you would start off, of course, with the first lens. So you would say first, and you would need to find your DI. So you have your DO, you have your F. So 1 over F is equal to 1 over DO plus 1 over DI. So 1 over DI is equal to 1 over F minus 1 over DO. So the first lens is down here, number 1. So it's going to be 1 over 6 centimeters minus 1 over 8 centimeters. Common denominator would be 24, the lowest one. So 4 over 24 minus 3 over 24 would be 1 over 24. So your DI1 would be 24 centimeters. So that means from this lens, there is an image somewhere back here that is 24 centimeters away. and this image becomes the object of your new lens. So if you know this image is 24 centimeters from first lens, then you should be able to figure out how far is your object number 2 from your second lens. The whole length is 40, 40 number minus 24, so DO2 should be 40 centimeters minus 24 centimeters. So DO2 should be higher order math, but perhaps you will get 16 centimeters. So now you have F2 and you have DO2, so you can find DI2. So 1 over F2 is equal to 1 over DO2 plus 1 over DI2. So 1 over DI2 will equal 1 over F2 minus 1 over DO2. So 1 over DI2 will equal, F2 was 12, so 1 over 12 centimeters minus 1 over 16 centimeters. I think common denominator is probably 48. So 4 over 48 minus 3, what's that, centimeters? 3 over 48 would equal 1 over 48. So DI2 would equal 48 centimeters. Okay? Now, once you have that, now you can actually find the magnification. Like, how well is this this microscope magnifying? So M1 will be equal to DI1 over DO1. So DI1 was 24, and DO was 8. So M1 is 3 times as big. M2, DI2 over DO2, DI2 48 centimeters, DO2 16, was it? Yeah, 16 centimeters, magnification 2, a coincidence 3 times. So then to get your total magnification, if you remember from those of you that took bio, it's just M1 times M2. So 3 times 3, your total magnification will be 9 times as big. Okay, so that's how you do compound lenses. So I'm going to give you a second example to try here, and then there's one in your textbook. Okay, so example number 2, there are 2 lenses. I'm trying to find the edge of my page. Whoops, let me go. Why is this not writing? Okay, I only have 2 minutes here. Pen, be good. Example number 2. All right, so again, 2 lenses. The distance between the 2 lenses this time is 27 centimeters. This is lens number 1, and F1 is 10 centimeters. And the object is, DO1 is 30 centimeters away, and its height is 4 centimeters. F2 is 9 centimeters. Okay, and so then the question would be, where is the final image, and what magnification does this have? Okay, and I guess I could also say what's the height, but who cares? So I want DI2, and I want M total. Okay, so try that one. And then on page 389, numbers 17 and 18. Okay, so just 3 questions for homework, but you also have other things to work on, of course. Read your lab and stuff, okay?